In this video, we will be looking at the Cartesian equation of a plane. So we know that the Cartesian equation of a line in R2 is ax plus by plus c equals 0, where x and y represents any point on that line in that two-dimensional space. And the coefficients of x and y, meaning a and b, represent the normal of the line, and the normal is the vector that is perpendicular to the line. Likewise, in three-dimensional space, we have a Cartesian equation of a plane, and that is ax plus by plus cz plus d equals 0, and this time the coefficients of x, y, and z represent the normal, and this is the vector that is perpendicular to all vectors on that plane. And the normal is vector ABC. And the reason we have a Cartesian equation of a plane in 3D for a plane and not a line is because in order to be perpendicular, to have a certain specific perpendicular vector, you need two vectors for that. Because we've learned in the past that when you take the cross product of two vectors, you get that perpendicular one. But when you have a line in 3D, you only have one direction vector. Whereas for a plane, we have two direction vectors, and that's perfect for getting a perpendicular one. So let's give this a try. Determine the Cartesian equation of a plane with a normal of -1, 2, 3 and passes through the point 1, 2, 2. Well, when we're given the normal, we have ABC. So we have the coefficients of x, y, z. So this is what we know so far. And now the only missing piece of the puzzle is D, which we can solve for by plugging in our point for x, y, z. So we'll have -1 plus 2 times 2 plus 3 times 2 plus d equals 0. And that's -1 plus 4 plus 6, which is 9. And when we bring the 9 over, we get -9. So that our Cartesian equation is -x plus 2y plus 3z minus 9 equals 0. Now, having this negative coefficient for x isn't great, so I'm just going to divide or multiply everything by -1. And that will just change all of my signs. There's my Cartesian equation of a plane. So in this example, we were given the normal directly. Determine the Cartesian equation of the plane containing the points A, B, C. Okay, well, I know for the Cartesian equation, I need the normal and I need a point. I have lots of points to pick from, that's great, but I need the normal. To find a perpendicular vector, I need two direction vectors, because then I can take the cross product. So we're going to start this question off as if we're finding the vector equation and we're looking for those two direction vectors. So I'm going to look for vector A, and I'm just going to use points A and B. So I'm going to find vector AB, which would be 0, -1, 2 minus -1, 5 minus 0, to get -1, 3, and 5. There's my first direction vector on this plane. And for the second one, I'll use AC, but any combination would work. So for AC, I'd have 5 minus 1, 6 minus -1, 3 minus 0, to get 4, 7, and 3. Now that I have two direction vectors, I can find the normal, because the normal will be the cross product of A and B, because the cross product gives us a perpendicular vector. All right, so let me do the setup. 3, 5, -1, 3. So I'm starting from that middle component. And now 7, 3, 4, 7. So 3 minus 35 is negative 26. 20 minus negative 3 is 23. Negative 7 minus 12 is negative 19. So now I have A, B, and C in my Cartesian equation. Negative 26x plus 23y minus 19z plus d equals 0. And I can pick any of my points that I was given to help me solve for d. I'm going to use A. So negative 26, then 23 times negative 1 would be minus 23. Negative 19 times 0 is gone, so plus d equals 0. That's going to be negative 49, which when I bring over will be positive. So we'll have negative 26x plus 23y minus 19z plus 49 equals 0. And again, because of that negative coefficient, I'm just going to flip all of my signs. And actually, if I wanted to avoid this step, when I got my normal here, because I know there are an infinite number of normals, I just have to be a scalar multiple of this one, I could have multiplied everything by negative 1 and used those as my ABCs right away. All right, next example. Determine the Cartesian equation of the plane whose equation is that. And we're given the vector equation, which is great because it makes our job a little easier than the above question because we're given the direction vectors right away. And we just have to find the cross product between them to get our normal. So 0, 2, 1, 0, 3, 4, negative 1, 3. And now for the normal, we want 0 minus 6. We want negative 2 minus 4. And 3 minus 0. There we are. There's my normal. Now I can use that, but I think I'm going to divide everything by negative 3 to simplify my numbers. And my normal can also be 2, 2, negative 1. And that's what I'm going to use for my Cartesian equation. So 2x plus 2y minus z plus d equals 0. And now I need a point to plug in, and luckily we have that. Here's the vector that represents the vector from the origin to a point on the plane. So there's my point. 2 times 1 plus 2 times 2 minus negative 1 plus d equals 0. So that's going to be 2 plus 4 plus 1 is 7. Bring the 7 over, and we get negative 7. So our Cartesian equation is 2x plus 2y minus z minus 7 equals 0. So in these first three examples, we were finding our normal if it wasn't given to us, and we used our cross product and then plugged in a point to solve for d. What if we go in the opposite direction? Write the equation of the plane, and you're given the Cartesian equation, as a vector and parametric equations. Well, let's think about vector and parametric equations. They have two parameters for a plane. And I have three variables in here, so I can pick any two variables and set them equal to one of the parameters. So I'm going to pick y and z. So I'm going to say let y equal t and let z equal s. Me doing that, I've just created two parametric equations. To find x, I'm just going to replace y with t, z with s, and now I'll bring everything over, and I'm going to put the constant first, so 6, and then plus 2t minus 5s, and there's my third parametric equation. So I have three parametric equations, and now I can find my vector equation. Okay, my vector equation starts with vector r naught. Vector r naught is created by the constants. So for x, we have 6. I have no constants for y and z, so that's 6, 0, 0. Plus Now the direction vector that's attached to t, so 2, 1, and z doesn't have 1, plus s, -5, t doesn't have 1, and 1. And for all of these, s and t are any real number. And there we are. So for this, we can set any of our 3 variables equal to 2 of the parameters and then just isolate for the third. All right, parallel and perpendicular planes. Parallel planes will have normals that are scalar multiples of each other, whereas perpendicular planes, if you take the normals and do the dot product, you'll get 0. Similar connection as we saw with lines. So find the Cartesian equation of the plane parallel to this, 2x minus y plus 5z minus 6 equals 0, and passes through the point 2, 6, -5. Well, if we know that our planes are parallel, their normals have to be the same. So they're going to share a normal. 2x minus y plus 5z. The only thing they're not going to share is that d value, and we'll solve for it by plugging the point in. So 2 times 2 minus 6 plus 5 times -5 plus d equals 0. So we have 4 minus 6 minus 25 plus d, which is -27. Bring that over, we get positive 27. So here's our parallel plane passing through that specific point. Determine if the following planes are parallel, perpendicular, or neither. Well, we need to look at the normals. So the first normal is 3, -1, 5. The second normal is -2, 4, 2. These are definitely not scalar multiples, and I can show that by testing out, let's say, k times n1 equals n2. So I'd have k times 3 equals -2, and for that, our scalar would be -2/3 for the x component to work. And then if I try it on the y component, I'd have -1 times k equals 4, and k is -4. Those are different. So there is no scalar multiple to make these parallel. All right, and then to test for perpendicular, I'm going to test the dot product. So n1 dot n2. Well, dot product, remember, we're going to multiply the x components, so -6, then the y components, so -4, and then the z, plus 10, and I got 0. And 0 for the dot product means our planes are perpendicular. All right. Final thing, finding the angle between 2 planes. So bouncing off of this dot product, we know that the dot product between 2 vectors, let's just say the normals, because those are the vectors we have, would be their magnitudes times cos of their angle. So if we wanted to isolate for cos theta, we divide both sides by the magnitudes to get this little formula. We've used it in the past to find angles. So if we want to find the angle between 2 planes where they intersect, then we can just do the dot product, divide by the magnitude of the normals, and then take a cos inverse. So find the angle between these planes. So I'm going to first identify my normals. 2, -1, 6. And then 2, there's no y component, so 0, and then 1 for z. All right, so cos theta equals dot product first, 2 times 2, plus 0 times -1, plus 6 times 1. So a dot product of 10. Now the magnitudes. 2 squared plus -1 squared plus 6 squared, all square rooted for the magnitude of the first normal. 2 squared plus 0 squared plus 1 squared for the second normal. So if we simplify, we have 10 over the first magnitude is 41, the square root of 41, and then the square root of 5. We can simplify this further by multiplying 41 times 5 to do square root of 205, or you can just take a cos inverse of this fraction right away, which is what I'm going to do. And I get approximately 46 degrees as the angle between these two planes. And that's it for our Cartesian equation of a plane.